events A1, A2, A3 through AN. Okay? Different events defined in the same sample space. And we are interested in the probability of all of these events happening. Okay? The probability that all of these events happen can be found by multiplying the probability that the first event, A1, of course, A1 is any arbitrary event in this group of events, in the set of events. Of course, it's not the choice of which set to put here first is arbitrary. Probability of A1 times the probability that A2 happens given A1 happened times the probability that A3 happens given A1 and A2 happened, etc. Remember, we briefly mentioned the example. Okay, what is the probability that you pass the courses EE 201, 202, and 311, all of these courses? Well, you first have to pass 201. Given that you pass 201, what is the probability that you passed 202? Given that you passed 201 and 202, what's the probability that you pass 311, for example? Or what is the probability that you get 3 heads in a row in 3 coin tosses? The probability of getting the first head times, given that that happened, the probability of getting the second head times the probability of getting the third head, given that the first 2 were both heads, etc. Let's do a more proper example. Oh, okay. Have you thought about how to show this result? Let's briefly show that that's true. Well, I'd like you to first think about the probability of AN, of the event AN, given that the events AI, maybe let's switch to black. Given that the events AI, I from 1 to n minus 1, all happened. Okay? What is this? Last time we defined conditional probability. The conditional probability of this given this is the probability of this intersection this divided by the probability of this, right? Probability AN intersection AI's, I from 1 to n minus 1, divided by the probability of the intersection of AI's. Okay? Now, from here, by cross multiplying, we can write the probability of intersection I from 1 to n AI's as the probability of the intersection of AI's, I from 1 to n minus 1, times the probability of AN given intersection AI's, I from 1 to n minus 1. Okay? What's next? What's next? We were able to express this, what we're looking for, in terms of this product, which already appears here, and this. All we need to do is to expand this and show that we can get to this whole product. Okay? Well, we can do that recursively because we've already shown the expansion of the probability of intersection AI's. Let's apply that here. Let's apply that to write this as probability intersection AI, I from what? 1 to n minus 2 this time. Okay, because we've shown it for any n. So let's use it here. Probability A n minus 1 given intersection AI's, I from 1 to n minus 2. Okay? So if you go recursively like this, eventually you end up getting this expression. Any problem? Alternatively, you could have taken this as the induction hypothesis. It's trivially true for n equals 1 by definition of conditional probability. And you can show by induction that this holds. Okay? And, after all, this is quite intuitive. Even before you took this class, before you started taking this class, I'm sure you had a notion of chain rule. And let's apply it to this simple example. There are two balls in an urn labeled 0 and 1. So there's a ball with a label 0 on it. There's a ball with a label 1 on it. Okay? And we draw a ball. Okay? The result is either 0 or 1. If it's 0, which happens with probability 1/2, the balls are identical. I'm just reaching into the urn and picking a ball at random. Let's model this as equally likely events, 0 and 1. Okay, with probability 1/2, the ball I draw is 0, labeled 0. And with probability 1/2, the ball I draw is labeled 1. Now, if it's 0, the ball is put back into the urn. So now you have an urn composition that's the same as before. But if it's 1, another ball numbered 1 is put in the urn together with the drawn ball. So now the urn composition has changed in favor of 1s. Okay? We repeat this operation. Again, draw a ball. It's 0 or 1. What are the probabilities? 1/2, 1/2 in this case. Here, draw the second ball. What are the probabilities? Drawing a 0 has probability 1/3, because only 1/3 of the balls in the urn are labeled 0. But there are 2 balls out of 3 that are labeled 1. Okay? And you repeat this operation. If you get a 1, you again put another ball labeled 1. Okay? The question is, you repeat this 3 times. A ball is drawn the 3rd time. What is the probability that all the balls are labeled 1? Okay? We'll use chain rule, obviously. The probability of drawing 1, 1, and 1. What is this? Well, first, you need to draw the first one. Okay. What is the probability of drawing a 1? 1/2. Given that happened, now you need to draw another 1. What is the probability of that? 2/3, right here. This 2/3. Given that you draw a 1 and another 1, what is the probability you again draw a 1? 3/4. Exactly, that's it. So the answer is 1/4. Any questions about this? No? Is this clear? Everyone? Okay. So, okay. So a very important consequence of the definition of conditional probability is something we use all the time in solving probabilistic problems. That is the total probability theorem. I sort of gave you an introduction to this without naming it. And so here's the point where we name this result. This is the idea of divide and conquer. Okay, sometimes it's easier to compute the probability of something by dividing it into small, manageable pieces. Okay? very useful idea. So here's how we do it. We are wondering about the probability of the event B. Event B is a set, as you know. We partition this set into A1, A2, AN, an arbitrary number of sets. These sets have to be disjoint inside B. They may be completely living inside B, that's okay. They may be subsets of B. But if they're not subsets of B, they have to be disjoint inside B. Okay, so AI intersection AJ is empty inside B. Okay, that's so how do we use that? We use that to compute the probability of the event B. Probability of the event B. Let's draw this Venn diagram. For simplicity, let's assume that the AIs are A1, A2, A3, etc. are subsets of B. So I've partitioned B as A1, A2, A3, A4. Okay, suppose N is 4. They are disjoint and they together completely cover B. Okay, so the probability of B is the probability, okay, A1, let's see, A1, union A2, union A3, union A4. Okay? In other words, the probability of B can be written as the probability of A1 times probability B given A1 plus the probability of A2 times the probability B given A2 plus the probability A3, probability B given A3 plus the probability A4, probability of A4 times probability of B given A4. Now, do you understand how we go from this point to this point? Yes. Why? Because A1, A2, A3, A4 are disjoint sets. In fact, A1 intersection B, A2 intersection B, A3 intersection B, and A4 intersection B are disjoint sets. So the probability of their union is the sum of their probabilities. So let's write the intermediate step now. The probability of B is probability of A1 intersection B plus the probability of A2 intersection B, etc. Okay? But what is the probability A1 intersection B? Use the definition of conditional probability. This is the probability of B given A1 times the probability of A1. That's the probability B given A2 times the probability of A2, and so on. Okay? So this is called the total probability theorem. Now, any questions about how we derive this? So you see from here that it is enough for A1 intersection B to be disjoint with A2 intersection B. Okay? A1 and A2 may be not disjoint outside of B, but they have to be disjoint inside B. Okay? So a common partition that we often use is one set A and its complement. Okay, so take any set A from the sample space and use A and A complement as the partition. Okay? So probability of B is probability B given A times probability A plus probability of B given A complement times the probability of A complement, right? Quite obvious. Because, for example, I'm trying to compute the probability that I get 2 heads in a sequence of 2 coin tosses. Okay, I can condition on the first toss being heads or tails. Okay, the first toss will be either heads or tails. These 2 events are a partition, okay, of the sample space, and they're complementary events. What is the probability that I get 2 heads, given that the first one is head? I can compute that. What is the probability that I get 2 heads, given that the first one is tails? This one goes away in that example. This one is 0. So that is, immediately I got rid of this part. And you can see how the total probability theorem is making computation easier. Okay, so let's try to apply this to a fun example, the Monty hole problem. This is example 1.12 in your textbook. Okay, let me remind you the problem. There is a prize. There are 3 identical doors. Behind one of those, there's a prize. Okay, you are told to pick a door, and the host then opens one of the remaining doors that has no prize behind it. Okay, at this point, you have the option to switch to one of the remaining doors that have not been opened, or keep your original choice. Okay? The question is, would you stick to your original choice, or would you switch? Okay? So the first question is, what is the better strategy? To switch or to stick to your original choice? What is a better strategy? Okay, so let's try to use the language of probability theory for this example, and in particular, let's try to use the total probability theorem. Okay, so I'm going to define the event B as the event of switching. Okay, so this is the event B. Okay, and of course, outside the event B, which is B complement, is keeping my original choice. Now, I'll also define the event A as the event of winning. Okay? Now, are A and B disjoint? No. Okay, I can switch and win. I cannot switch and win. So they are, in general, sets with a non-empty intersection. So, for example, this is set A, and this is set A complement. A and A complement partition the sample space. Okay? And they are disjoint. Okay. So, first of all, let's answer the first question first. Should you switch? Okay, let's compute the probability of winning given I switch. This is essentially given in the question. This is P, A given B. Now, in the event that I switch, okay, I win if my original choice was wrong. Okay, do you see this? What is the probability that my original choice was wrong? 2/3. So this probability is 2/3. Okay? Therefore, the probability of winning, if I do not switch, which is the probability exactly of the event of my original choice being the correct one, that's 1/3. Let me write this in this by using this notation. This is the probability of A given B complement. Okay, that's 1/3. Okay, so we answered the first question. What is the better strategy? Switching is the better strategy because the probability of winning when you switch is 2/3, and probability of winning if you do not switch is 1/3. So switching is the better strategy. So here is an interesting proposition. Let's adopt a randomized strategy. Randomized algorithm for switching, meaning I toss a coin, fair coin. If it comes up heads, I switch. Otherwise, I keep to the original door. Okay? Show that as a result of this strategy, my probability of winning is 1/2. Okay? It's better than not switching at all. It's worse than always switching. It's a randomized strategy. Maybe it makes you feel better in some way. Okay. How do we do this? Any suggestions?
Use the total probability theorem.
Yes. How?
We'll multiply the probability of winning in case of switch with the
Probability
probability
of
of
switching.
which is
Very
the
nice. Okay. So think about the randomized, thanks Deniz, randomized strategy. In the randomized strategy, the probability of switching is 1/2. The probability of switching is 1/2. The probability of not switching is 1/2. So the probability of winning in the randomized strategy is the probability of winning given that I switch times the probability that I switch plus the probability of winning given that I don't switch times the probability of not switching. Okay? What is probability of winning given I switch? That's 2/3. What is the probability that I switch? 1/2 plus probability of winning given I don't switch is 1/3, and this is 1/2. Okay, so this makes 1/2. Okay, any questions? I'm sure at this point, at least a few people have a question. Or maybe it's not clear. Maybe you lost it at some point. Yes, please. Excuse me? This 2/3. This one, right? Okay. Now, suppose I will switch. I first pick a door. There are 3 doors. One of them has the prize. Okay. Now, when I switch to this. Okay. Suppose I will change my original choice, meaning I switch. What is the event that I win by doing that? I only win by switching if my original choice was wrong. Because if my original choice was the correct door, if I switch, I will not win. Right? So I win by switching if and only if the original choice was wrong. And the probability of the original choice being wrong is 2/3. Okay? All right. Any other questions? All right, so maybe this is a little of, somewhat of a puzzle. We'll work out more straightforward problems, but I like including these puzzles because they're sort of interesting. Sometimes they are sort of controversial. So I'd recommend that you focus on the more straightforward problems rather than these puzzles. Okay, once we define show Bayes' rule, okay, we'll be able to solve even more interesting problems. This is a rule for combining evidence. What do I mean? Okay. Now, let's begin with the definition of conditional probability. Probability of A given B. Okay? Now, if you weren't following up to this point, you can restart at this point. Okay? We'll just start with the definition of conditional probability. The probability of A given B is probability A intersection B divided by the probability of B. Any problem with this? No. This is the definition of conditional probability. I can rewrite this as PB given A is probability A intersection B divided by P of A. What do I gain by doing this? What I gain is I can express the probability of this intersection as this product. Okay, so cross multiply these two terms to get the probability of A intersection B as the probability of A times probability of B intersection A, B given A, okay, and the denominator is the same as before. We've just proved Bayes' rule, okay. This is called Bayes' rule, and it's the basis of a lot of different problem-solving techniques in estimation, in pattern recognition, image processing, tracking, etc. Okay? Probability of A given B is probability of B given A times probability of A divided by probability of B. Why would this be useful? Under what conditions would this be useful? Well, here's an example, okay? There are two known criminals, okay, in the, let's say, the police database. Okay, a crime has been committed. Okay, a certain crime has been committed. There are two criminals that are being suspected of this crime. Okay, they are both, let's say, a priori believed to be 20% likely to commit this crime. Okay, 1/5 probability is the best guess we have for these two criminals, each committing this crime. Okay, and they are a priori, in the absence of any evidence, they are 50% likely to be near the site of the crime at any given time. Okay, but as a result of an investigation, okay, why is an investigation done? To gather information, to gather evidence. Okay, as a result of the investigation, it is revealed that criminal A was near the site of the crime at the time of crime, but Y was not. How does this change the posterior probabilities of committing the crime for criminal X and criminal Y? Okay, I guess first one is easy. For Y. Maybe I should, at this point, explain you the terms a priori and prior probabilities, that is prior and posterior, okay? Prior probabilities. These are the probabilities before we make the observation, before the investigation, before observation. Let's say. What are they? The probability that, let's see, the probability that X commits the crime is, the prior probability of this criminal X committing the crime is 20%. Okay, 20%, if you want, 1/5. Okay? The probability that Y commits the crime is, again, 20%, which is 1 in 5. Okay? Posterior probabilities. Posterior probabilities. Meaning after we gather some information, after we make some observations. What are they? The probability that X committed the crime, given that X was near the site of the crime. Okay. How do we compute this? We know, what do we know? We have Bayes' rule. What does Bayes' rule say? Bayes' rule says, if you don't know the probability that X commits the crime given that he was near the site of the crime, you can switch these events around. That is, you can write this as the probability that X was near the site of the crime, given that X committed the crime, times the probability, prior probability of X committing a crime, committing this crime, divided by the probability of X being near the site. Okay, do we know everything? All the probabilities in this expression? Yes, we do. So let's compute. The probability that X was near the site, given that it committed this crime. What is that probability? That's 1, right? Because it has to be near the site if it commits. Let's think in simple ways, okay? Let's be simple-minded. Given that it commits the crime, it was near the site. He was near the site. That's 1. What is the prior probability that X commits this crime? 1/5. What is the probability that X is near this site in general? 1/2. So what is the posterior probability? 2/5, which is 40%. So the investigation increased our suspicion that X is the criminal. Let's see what the investigation did for Y. Let's do it here. What is the probability that Y committed the crime, given that Y was not near the site? Again, let's think in simple terms. If it's not near the site, if he's not near the site, he cannot commit this crime. This is the probability that Y was near the site, given Y committed this crime, times the probability that Y was not near the site, given that Y committed this crime, times the probability that Y committed this crime, given the probability that Y was not near the site. Now, do we need to compute everything in this expression? No. Because this, the probability that Y is not near the site, given that it committed the crime, is 0. This is a very fancy way of saying that if you can prove that he wasn't near the site at the time of the incident, he's innocent of the crime. Okay? The probability reduces to 0. He's not a suspect anymore. Okay, this is something that you knew even before taking this class. But this is the Bayesian thinking, okay, in the language of probability, applied probability. Okay. So, these are posterior probabilities. The posterior probabilities are different from the prior probabilities. Of course, sometimes the evidence does not carry any information. In that case, the posterior probabilities are not different from prior probabilities. Can you tell me the time? Okay, any questions? Yes, please. Here? Okay. Let's see. I'll try. Okay, I'll try. I don't know how good this will be. Let's make an attempt. Okay. So X is either guilty or not guilty. This is X complement. Okay, X is not guilty. Let's call this. Let this be the event B. Okay, B is X is guilty, and B complement is X is not guilty. Okay. Now, if X is guilty, X has to be near the site of the crime. But if it's not guilty, it may or may not be near the site of the crime.
He
Okay?
wasn't near the site. Could he be commit the crime?
No. So the set A is, and this is A and this is A complement. A is X was near the site of the crime. Okay? B is a subset of A. Okay? If B happens, A has to happen. This is the model we have for this problem. Okay. Any other questions? Yes, please.
Başlarken %20-20 iken sonradan %40-0 olması bir tesadüf mü yoksa bu şekilde toplamların aynı mı?
It's because of these given numbers. You know, it's a. If you're interested, try this example with different numbers and see how things can, how interesting things you can get. Okay. So, Bayes' rule is often applied to events AI that form a partition of the given event B. Yes, please.
X was near the site'ın oranı %10 olsaydı eğer cevap 2 çıktı. Yani X was near the site'ın oranı eğer %10 olsaydı.
So the prior probability of X being near the site is 0.1, you're saying. So in that case, your example violates this Venn diagram. The probability of A has to be bigger than the probability of B. Right. Good question, though. So basically, in the design of this problem, we implicitly assume that the probability of being near the site of the crime is bigger than the probability of the prior probability of being guilty. Okay? So, let's continue. Okay. So, you know, select some events AI that are a partition of the given event B. The probability of AI given B, use definition of conditional probability. This is the probability of AI intersection B divided by the probability of B. Use Bayes rule. Probability of B given AI, probability of AI given probability divided by the probability of B. Now the third step is to write the probability of B in the denominator using the total probability theorem. Okay? So what you end up getting is a sum of terms, one of which is the numerator itself. Okay? Let's just apply this on an example. This time, not a fancy example, straightforward example. So consider two tosses of a six-sided die with equally probable faces. Given that the sum of the two tosses is 7, what is the probability that the first toss is a 3? Okay, so let's write what the event B is. B is the event that the tosses sum to 7. Well, what are the ordered pairs that are included in this event? 1, 6, 6, 1. What else? 2, 5, 5, 2, 3, 4, 4, 3, and that's it. What is the probability of the event B? All pairs are equally likely. B has 6 outcomes in it. Out of 36 possible outcomes when you toss a die twice. Okay? So 1 over 6. We use the discrete uniform probability law. You'll remember it from last lecture. Okay. Now, what is the probability that the first toss is 3, given that B happened? Let's apply Bayes rule. This is the probability that B happens, given that the first toss is 3. Let's use a shorthand notation for this. Let's call this A3. Okay. B given A3 times probability A3. Now in the denominator, we can sum probability B given AI times probability of AI. I going from 1 to 6. Okay, because A1 is the event that the first toss is 1, A6 is the event that the first toss is 6. Okay, so let's compute this. What is the probability that the sum is 7, given the first toss is what? 3. That's 1 over 6, because the only way it happens is that the second toss is 4. Okay, so 1 over 6 times the probability of the first toss being a 3, which is 1 over 6. And in the denominator, all the terms are actually, you can show that, let's see. Now, given that the first toss is 1, it's again 1 over 6 times 1 over 6. If the first toss is 2, again 1 over 6 times 1 over 6. If the first toss is 3, again 1 over 6 times 1 over 6. If the first toss is 4, again the sum can be 7. If the first toss is 5, so basically we have how many terms here in the denominator? 6 terms. So 1 over 6. But, okay, so this is a fancy way of answering this problem, of course, because we wanted to apply this form of Bayes' rule. But we can verify our answer. How? Given that B happened, B is the new universe. In this new universe, what is the probability of the first toss being 3? There is only one out. This is represented by this outcome, 3, 4, out of 6 equally likely outcomes. So 1 over 6 is the answer that we expected anyway. What's the time, please? So I believe we're out of time. The next 2 examples are very interesting. Please try to work them out yourself. The first one is a radar detection problem. And the next one is a medical false positive puzzle. Okay? I'll see you next time.